Elon instead. Start editing. Necessary. Numerical search. I need this. Come on, machine, wake up. Machine. This is okay, this is fine, this is fine. Everything fine. What I need? I need my tape. Okay, let's go. I have prepared something for today. It's an AC network. Small experiment. I have a source of AC. I have my voltmeter here. I have an instrument called power factor meter here. Next one is a watt meter. It's here. I have an ammeter. Here I will have a split. Second ammeter switch and simple bulb. It's one, and from the split I have what I have. I have another ammeter. It's number 3. It's this one. With a pair of switches And as word I have capacitor and another. I have this. Can switch it on. Yes, it works. I also have connect and water. More connection for the gut of connection. I have a scope showing two signals. Voltage and current. Yeah. I may come closer. Closer to my instruments. Like this. So, I have 100 volts network. Here it is 100. I have this nice load. My current is 0.8 amps. Here full scale is 5 amps, so it's also 0.8. And power, what it is, 40 should be multiplied by 2, approximately 80 watts. Everything fine? Or you see something wrong? Nothing wrong. If I double the load, I have double. Now this and this switch are on. What we see? 0.8 here, 0. It's 78 here. Double current here is a sum. First kilovolt in working and double power here. Everything fine? Fine. Now, what I'm doing? I'll do this. I have now switched on this capacitor. Current flows, voltage present, current flows, yeah, here it is, 0.8 amps, and total current goes 0.8. But power is 0. 0. Strange, isn't it? Current, the same, 0.8. Voltage the same. Power, 80 watts. Something wrong here. But here's my question. I got, when this is plugged, 0.8 ohms. Yeah? When this is on, 0.8. 0.8, what will be if I plug both? 0.8 and 0.8. But 1.6?
Yeah.
You agree? It's 1.6. What do you think? What will happen? Take a look. Right one, 0.8. Left one, 0.8. If I plug both, what will happen? Also, you agree? 1.6? No. What? What we will see? Oops. Only one. 1.1. Exactly. Why? What's going on here? Something strange, isn't it?
Yes.
Here is current of active voltage, current. Let me put my camera in different position. Bit brighter. You can see something. Here we have a pure active volt, 100%. You can see voltage and current in the, they are in the same phase. No angular shift between them. The red line is an instant power, the multiplication. You can see it has a double frequency, and if we summarize for one period, we will see what its sum is positive. If we sum all these areas, we will see plus. So, power is positive, we see it here. As a 40 multiplied by 2, 80 watts. Capacitor. See where the current is. It's shifted by 90 degrees relative to voltage. And an instant power, if we sum for one period, well, one period is a 20, one this is a period, this division. So within one division, up, down, sum is 0. And we see 0 power here. If we apply both, case current is shifted relative to voltage. Power, something goes negative, but overall it will be positive. You can see it's a positive. At this moment, two active and one capacitor. The same situation. This angular shift. Why? What happens? There must be something. What your electrotechnics theory says about it. capacitors. Someone should burn all these capacitors. Why? Why such strange thing happens? Look. Bulb and bulb. 0808, sum. Everything fine. Sum double. 1 is just below 2. 2 of them just near capacitors. 1 capacitor, 2, 1 bulb is 3, 2, both of them, not 4, but somewhere. What's going on? Difference, 2 bulb and capacitor. What your electrotechnics theory tells about you? You completed this course of electrotechnics theory, basics.
Only theoretical course.
Theoretical.
Yeah, that's
What theory says about it? Where is my... Oh. Paradox, isn't it? I made this for the Open Doors Day for school children. But it's a good demo. Here it is, it's for what I have, generator, capacitor. I make a mechanical job, yeah?
Yeah.
And my job converted to electricity. And you can see, it's way, I do nothing, but it still has a charge.
Yeah.
Why? Because capacitor can store energy. Yeah. I have charged capacitor, and it keeps energy. I may use it as energy.
Okay.
It charges until reach an ignition level and has energy. I use this energy. So capacitor store energy, and you see voltage rises, oops, it blinks. Voltage rises, it blinks. Rises.
Саша, вы знаете, что вверх? Там началось вверх.
Конечно.
Вверх пасть. Вперед вышка. Как не вы, потом мы заблокируем.
Ничего не знаю. Мне просто нужно, ну, это... Год.
Вам осталось только такое. Ага. Только нормально. Ну, так вы делаете, как у меня, там паспортная ВПС, ну, паспорт, так, чтобы не дергать вас.
I can use an analogy, but we have, let's say, basin with the water flow in. If the water flow is current and level of the water is a voltage, cross section will be capacitance. So level of the water is a sum of all water came in, but we have a proportion, it's a cross section of the, we can say what capacitor voltage is capacitance, 1 against capacitance, sum of all charges, it will be sum of all charges in full. Yeah?
Yeah.
In such case, if we have voltage, as in my scheme, being sine divided by t and multiplied by time. Double P is clear, period, T capital, here, from this point to this. Distance for 50 hertz, network, T capital is 20 milliseconds. What will be it's our voltage. We have, what we have? Source, capacitor, yeah? Capacitor voltage equals to the mains voltage, yeah? So, what should we do to get current? Take a derivative to get rid of integration. If we take a derivative from the sine, what will we get? A sine. So, what's the idea? Here, voltage is delayed relative to current. Because capacitor has inertia, and its inertia is defined by its capacitance. But in case of stable regime, I would like to show you one thing. 1 second. I will bring my camera in some kind of normal position. I will compress time. Here we see inrush regime. It's a power up of the network. I have recorded. maybe 1 second I will make it a bit clear. Like this. You see what's going on with current? Voltage. See change. See what happens with current. It's inrush of the transformer. See the form of the current. See this. I have recorded with inrush, switch on moment, with transient. This part is contains also 3 components. Now we talk about stable regime, about this part. This part is developed by 3 regime. This one is stable or enforced when the transient is ended. Transient, you see, it's an inrush. This part is more complicated, but we can separate overall regime in 2 parts, in 3 components, which develop this part, and stable or enforced component, this part. We are talking now about stable, when transient is ended. You see, now everything's stable. Yeah, I need a single sequence. Here is a unstable. After I switch on, we have an inrush or switch on transient process. Now we will speak about, let's say, easiest part. But in reality, 99%, camera.
Okay.
In 99% we need this part. Anyway, we cannot calculate transients, or we cannot calculate or analyze overall regime until we know this stable part. The free part comes as addition to this stable. So now we are here, where there is no inrush, no transient component, everything is stable. So network, at a switch on moment, there are changes, and then networks came to some kind of equilibrium, to some kind of stable regime. Yeah. Now it's in stable regime. So we speak on stable regime. And on stable regime, what we will see, we can see what capacitor voltage is delayed relative to current, because capacitor needs to charge. Capacitor has inertia. It can store energy. This means, what if we speak relative to voltage, blue line current comes, I can see. Here, pure capacitor current. Blue line comes first, because voltage is delaying relative to. It's in stable regime, in transient it's different. But here in stable regime, what we see, what current appears first. Here is the problem. In stable regime, we have shift between voltage and current. For capacitor, if I switch to active load, no shift, everything simple. But when capacitor is here, I have problem with this shift. I need a technique to solve it. And key element, I should avoid trigonometry, because it's very labor consuming. How can I avoid trigonometric function? I don't need, I will take different, I will have cosine, but it will not help me to solve network. It will be complicated. What should I do? I can open one document. How can I switch? Yeah. I have two persons here. Over heavy side, yeah, the guy who invented idea how to deal with this network. Idea of symbolic or operational calculus. And real developer, here in the middle, it's picture from RCI, Radio Broadcasting Center, commissioning. Here in the middle stands Charles Pratel Steinmetz, who in 1893 published a paper, Complex Quantities and Their Use in Electrical Engineering. This was a key breakthrough in AC network solution. Key idea by who's this guy? Near him. Yes, this one. Albert Einstein. And about this person, there are, how to say, different opinions. One believes that it's Nikola Tesla, and but no, Nikola Tesla could be here because there was Steinmetz, Einstein, and other persons who don't like him. So it's a Carson, not a Tesla. It's unclear, Tesla or Carson. Anyway, our hero who developed.
So
Yeah.
I have one doubt that the three places are similar voltage, same voltage, right?
We will see with three phase we will need one more transformer.
Okay.
We will our next subject will be three-phase network, but I cannot speak on three-phase network before
Okay.
I'm done with the one-phase network.
The yellow one.
Yellow one is voltage and blue one is current.
Oh, okay.
Yeah.
What about red one?
Red one instant power.
Okay. Now the current is 0.
Now when current is 0, because no load.
No load, yes.
We have some noises.
Yes.
Here, wait 1 second. This one. Active load 80 watts.
Okay.
Instant power positive.
Yes.
One capacitor. We have current, we have voltage, but we have no power because integrating all this we will get 0. And mixed load,
Okay. Positive.
we have power of this. I can plus energy going to capacitor, from capacitor to capacitor, from capacitor. We have current and energy going up to capacitor and down from capacitor. It discharges to network. Again, energy goes
Up and down.
into
Yes.
and next time hop up
Down.
to the network. This way, and this way, and this, and return.
0.
Sum is 0. It's like oscillation.
Awesome.
Without any
No.
without any usable product. Let's say it's give sum is 0.
Yeah.
It's just
Awesome.
going up, down, left, right, left, right. With active load, what's above
Fully positive. Yes.
line will go no, at the slightest heating. And part oscillating. Which part? See the difference?
Yes.
With oscillation, without. Okay, so what's the idea of Heaviside's theory and what Steinmetz has developed? Where am I? I need my table.
Sir, if I connect in that, what happened in this?
You see, it's waiting there on the table.
Okay.
You
okay,
see,
okay, okay.
here it's I have a red inductor
Okay.
already waiting.
Okay.
Beware, it's got part not attached. First idea of this technique. Somewhere in human mind exists a number what cannot be. It's 1i, 1, and it's a square root of -1. Impossible. Each number raised square will be positive. But if let's imagine what it exists. In such case, any number will have real part and imaginary. And we can use a complex plane +1 or real number and or imaginary. So let's say exists some x as a plus b. Case x, its real part a and its imaginary part b. Sounds strange, isn't it? But it's a plane of mind. At this time it's a plane of mind. In reality they are not exist, they are imaginary. Let's imagine what Rothschild donated me 1 million. $1 billion. In the imaginary I'm a billionaire, in reality, guy, you're an idiot. Take your shovel and back to work. The same thing I can represent in different manner. What can I use? I can use an absolute value and an angle. Yeah? Yeah. So absolute value will be square root of a square plus b square, and an angle will be arctangent b against a. Without arctangent. Or I can write what a is a cosine phi and b imaginary part is an amplitude sine phi. It's a simple trigonometry. Am I right?
Yes.
Yes. On the other case, we see what's the yellow line. Sine omega p, where omega is double p divided and waste U max. This distance will be U max. Take a look here and here. What do we see? Sine and sine. What was the Heaviside's bright idea? Let's assume what this voltage, real voltage, if I put my fingers here, I will feel it, is a projection to the imaginary arcs of some vector. Idea. Here goes up imaginary axis. This is vector. It stands like this. Light falls from the window. Shadow of this vector will be its projection. Vector rotates with the frequency of omega. It's an angular rotation frequency. So idea, what? Voltage sine omega is what this voltage, this yellow voltage is a projection of some imaginary vector rotating with the speed of omega. This is not enough. Key moment. We need to align all values, everything, in such way that will be possible to use Kirchhoff's and Ohm law as they are known for DC. For such usage, we need to do one more adjustment. Problem is, what if we multiply such voltage with the current, we will receive an instant value. This one. This is something like active load, something closer to DC network. We will get this one. We need area of. That's why one alignment was made. That it is an idea of effective value. To make all this calculus, or let's say mechanics, similar to DC network, special value, effective value introduced. Idea, if we have our AC voltage loaded with resistance, resistance will hit with the power P1. Load the same resistor with ideal DC source. It will also heat with the power to produce heat with the power P2. If P1 equals to P2, this DC source is equivalent to AC in power they produce. Meaning what? E squared divided by F equals to maximal square divided by F, integrating from 0 to period sine square omega t also we need an average this one goes, and we have this equivalent, or, one moment, we will see 1 divided by period square from 0 to time sine square, which leads us to divided by square root of 2. It's an RMS value of our voltage. We will get correct power if instead of real amplitude we will use RMS. It's done intentional to make our calculus close to DC network. And all these instruments, all these amperes, all these volts are RMS. Take a look what we have. Channel 1 RMS, 102 volts. What's the amplitude? You see channel 1, it has 100 volts in a per division. K is 100, K is 100 plus 40 approximate volt. So this distance is an amplitude, and here you can see it's calculated RMS. Effective value or RMS. It's done intentionally to make network similar. So going forward with the ideas of symbolic network. Voltage will be represented as a real vector like this, with its magnitude being divided by square root of 2. Current this current, active load, see the blue current, it has the same angle as a voltage, yeah?
Yes.
Yeah. So it will be O divided by R. Simple. More complex. Here is the capacitor current, which is derivative of, we have capacitance and derivative. Idea is to represent it with a vector. It's a capacitive current, and it is.
Sir, why producing the noises in the current?
Huh?
Why producing the noises? The blue line.
Blue line, this disturbance.
Yes, why?
Because network is not ideal. It's a result of network being polluted with noise of all kind of digital. Do I have one moment? Do I have it in English? I have a lecture on this, but is it in English? I don't know. It's inside the theory of signals. Harmonics flow in a power network. Wait 1 second. I can check. Do I have it or no? It will be O divided by reactive resistance of capacitor. Idea is to get this to correctly represent fact what capacitor stores energy, has inertia, and as a result of this inertia, current leads voltage.
Okay.
See this instrument. It's a measure of angle between current and voltage. Active load. Angle is 0. You see, 0 is here. It shows power factor is a cosine of the angle between current and the voltage. Numbers are value of cosine, but needle shows us the angle. Only problem, it has a 0 here, vertical. It should be it should be like this. But watch, I'm adding capacitor. See where it goes?
Yes.
Lead. It's a leading power factor. Yeah, leading into 0. Which way? One moment. I have a feeling it will be better. Voltage like this. Yeah. Now, if I have to put it, anyway, in such case I have
Now in this case,
no. It's
0 maybe down.
I have swapped voltages.
Okay.
Get it back. This is this is yeah, this is correct. This one is correct. Active load, lead, and to 0. So, to get this, I can use one thing. I need this resistance. What we know? What it will have negative proportion against capacitance. The bigger capacitance, the lower resistance. It's dependent on the frequency, because derivative from the sine will be cosine of the same angle, so it's frequency. And (90° in forward), it's like multiplying by if this is x, 90° forward, it's or division by minus here. So it will have introducing an imaginary resistance of capacitor, we will get Ohm's law. Current, this nice current, will be voltage divided by resistance, but this resistance will be imaginary. On the one hand, it's something strange, but Ohm's, we will get Ohm law in a complex form. It's an Ohm law. And what about Kirchhoff? Look here. Active current. We assume what voltage is real. I can do it. Case yellow line is a voltage. In real, and I assume what this line is a shadow of this vector. I can apply a yellow color to it. Now I have the blue line is a current of this bulb. It's okay. I will use red. Red is a resistance current being voltage divided by active pure real resistance. Can it? Well, do not store this energy. What's this? Current of capacitor. Current of capacitor it's the same. I use the same. Not I use the same. I have adjusted capacitance to produce the same current in magnitude as my one. So this is it being voltage divided by Xc. And Xc is 1 against omega C. Now, what will be sum of them? How do we sum vectors? I can do n. Here is the summary current. What you saw, not 1.6, but actually it will be 0.8 multiplied by square root of 2 because they are equal. Here, take a look. 0.8, 0.8, and the sum. This is 1, 1.2, something like this. Yeah? No, 1.4 is 1 by 4. If they would be 1, then we will have 1 by 4. It will. And here we have what we have? Less. We 1 by 4 multiplied by 0.8. Yeah. Here is the 1 arm. 25 division is 1 arm. 1 arm plus 2 more divisions. Something like this. Good idea, isn't it? But what about coils? Can we get a coil here? Here is my coil. Yeah, I have adjusted coil current to 0.8 amps. Here is the coil current. What do we see? Voltage, coil current. Not ideal. This is what coil's voltage as a function is inductance multiplied by derivative of the current. Why? Lenz's law, self-inductance. What about inductance? Where's my experiment? Have you seen this experiment in physics? Coil, inside the coil, and a steel core. So, no need to repeat. Yeah, you saw it. Really. Coil inside the coil, it should be connected to galvanometer. Right? See how it reacts to the current change in primary coil. You saw this. Yeah, due to changes in magnetic field. Key elements, its change should be
one part to another is transferring.
Yeah. And magnetic conductance increase effect. 17.2 millicurie. Oh, you saw it. And you understand why I'm writing this. What this means in our case? What if voltage changes on the sine law and L equals to its self-inductance, this means what to get current we need to integrate. So the current will be integrated of sine, it's minus cosine. You see, current is delayed or lagging relative to voltage. To reflect this, effect, I can erase this. To reflect this effect, so this is our voltage, current appears to be here. Lagging rotation goes this way. So we see voltage first, here on the freezer. First arrives voltage and then current. If someone stands here, what will we see? First voltage hits him and then current. Coils, reactive resistance.
So what about the angle? The voltage and current angle?
In ideal case, it will be 90. But real coil has losses So you see, it should go like this,
Okay.
and here we have small angle. I can try to measure it. No, it's a real coil with a real active resistance of the wire it's made of. Plus this noise is also active noise. Plus steel core also has a noise. 4, 4, 4, 4, 4, 4. Have an example of very good coil. Yeah, it should be somewhere. It should be in the box. Yeah, here's very good coil.
Very good, yes.
Without steel core, without losses, ceramic base. Again to reduce loss. And you see, massive wire. But it's only 11 millihenry. It's a small, it's for radio transmission. It's not suitable for 50 Hz. I need something. So XL being omega. If we take derivative, that's what we will get. Let's again take a look. Nothing. Active load 0.8 amps. Coil come on, I will make you 0.8. Coil 0.8 amp. What should be the sum? 0. If it would be resistor, it will be 1.6. But here, what it will be? Oops, this is some. This is my summary current. But if we take a look on power, 0. Without active part, and here I have added as active part, it will yield something positive. Come on. Use 0.8. All together, the same thing. We need a vectorial sum. There is one more element. Metal coupled metal inductance. If two coils are coupled magnetically, we can represent it inductance. Yeah. You saw it in reality.
I studied in the UG.
Heard something about it. Okay, if I have time, I have a demo. But now I need what I need. I need to go a bit forward. I need to show my ideas. Okay. I need to switch to my presentation. How can we solve AC network. With the help of Heaviside and Steinmetz science, we take this same, we can use technique extremely similar to DC net we used on DC network. First, take our schematics and select a base node. In theory, I can select anyone. In real life, I will need to take care what I'm selecting. But here it's a practice, so I can take any node as a base. I took this one. Here is the green triangle. You can see the green triangle. I have marked a base node. I'm assuming here is the zero voltage. Other nodes are numbered 1, 2, 3, 4, 5, and 6. Also, I need to assign numbers to branches, and not only number, I need also assign direction. It's on my wheel. So this will be first, and I'm assuming that it goes up. It's my choice. When I have everything, let's say, labeled or counted, I conduct nodal admittance I conduct first incidence matrix. I will calculate nodal admittance matrix later. But first I need to conduct first incidence matrix. It's a branch to node connection. So rows are number of nodes excluding base. There is no row for base node. And columns are number of branches. If branch inflows into node, I should write -1. If branch flows from node, I should write 1. This way, not in opposite. If I'm willing to use contour current techniques, or I need a second Kirchhoff, or I don't know why, I can also conduct a contour matrix. For contour matrix, I need to select the contours. Number of columns of M matrix minus number of rows in M matrix yields me a cyclomatic number or number of necessary contours. Here 11 minus 6 yields me 5. Yeah? I need to select 5 contours, 5 set of branches, what some imaginary travel can walk around. So I'm taking this one as a first, this one as a second. Here will be third one, number 4 and number 5. Okay, it's number E. I can also take something like this, or I don't know. I can select something like this. No one stops me. I just need to select 5 of them. For each contour, I need a number and a direction, walk around direction. When I have it, I can conduct, where are you? Yeah, here it is. Second incidence matrix. Where row is a number of contour and column is a number of branch. If branch falls in the contour, walk around direction, I write +1. If goes in opposite, I write -1. It's a network topology. Now, EMF vectors. Easy. It's connected by branch. So it's a column where row is a number of branch, as we did for DC network. And if EMF is in the branch direction, write it with the plus sign. If goes in opposite direction, write it with the minus sign. You will get something like this. Good. Next question, impedance matrix. Here, resistance, better use an term impedance matrix, will have real and imaginary part. For elements not storing energy, digit will be real. For elements able to store energy, or in electrostatic field as capacitor, or in magnetic field as a coil, there will be a complex value. If there are no mutual inductance, we fill only main diagram. So you can use a column vector where resistance are resistance, capacitors, here is a 31 microfarad capacitor. 1 divided by omega multiplied by capacitance. For coils,
Sir, I have the doubt in this section, sir.
sorry?
Impedance vector, table number 4, say how we can do that. 18 plus JW multiplied 10 e power minus 8.
Yeah,
how we can do it?
wait a moment, I'll show.
Yeah, I have
Wait one moment, don't worry, I will open a program text
okay.
for this. Now I'm in an idea, 1 second, I have it ready. It's waiting right here. And what else? Yeah, current sources. The same way as we do for DC network. We need 2 vectors for current sources. 1 per node. If current source inflows a node, write it with the plus sign. And if flows out of the node, write it with the minus sign. Simple. But we also need additional contour or this imaginary contour if we are willing to use contour current technique. This means that for each current source we need to set, define or assign an additional contour. I'm assuming what current of the source goes only here. Look, I have chosen 9th and 5th branch as a way for my current source. Here it is. Fake, you can say fake path. I just take what it will go here. And I will get this table. So it's by branch. If this imaginary current falls in branch direction, I should write with the plus sign. If in opposite, with minus sign. This is it. Now I can only perform calculus. I can use what m multiplied by n transpose produce 0 to check if my matrixes are coherent. I can also check, knowing what m multiplied by g should be equal to I vector. And then I use virtually the same nodal admittance matrix and nodal voltage equation as we saw on DC. I will get a system of linear equation. Currents can branch currents by Ohm law without any problem. Contour current, same thing as we saw on DC. I can get a contour resistance. They will be complex. The only difference, they will be complex. But the key core remains the same. With the help of this symbolic technique, I extend topological analysis of DC networks 2 AC space. Contour EMF, easy. Linear equation system, easy. Branch currents, easy. Voltages, easy. One moment, powers. What about power? If I multiply simple voltage by current, I will receive, not right, I will receive nonsense. To get full power, here power, as we saw, red line, consists of two parts. One yields positive, in my case positive heating, and one corresponds to just charge capacitor with discharge capacitor, a kind of oscillation of energy. It's called reactive power. Active power is real. It's real heat, real torque of the motor, something like this. Reactive power is a fake. It's a difference between instant power and real usable work. To get everything correct, current is, will produce a wrong result. Conjugation of the current should be used to reflect everything correct. This will get us everything correct. So idea, if I have voltage and, for example, lagging coil current, it's L plus R, yeah? This is angle phi. Power will be total power being Q multiplied by conjugation of the current. If I have some X with angle phi, its mirror is a conjugate X. So X, A plus D, X conjugate will be A minus dot B. This is apparent power. Here the same angle, and it consists of active part. That's what it's our heat. And reactive part reflecting this oscillating back and forward energy. One moment, I can. Switch, yeah. Voltage, current, angle, apparent power, same angle, active power, being U multiplied by E multiplied by cosine of phi, which is power factor. Here is written power factor, and it's cosine of the angle between the, I had this coil current, I have this active current, their sum is a full current, and it's full current multiplied by voltage given the apparent power, projection to the real P, and imaginary dot cool. Coil assumed positive, capacitor assumed negative. It's just agreement. So, what I need to do? I need to switch to my. Come on. Here. And what? And what is with mine? Wait 1 second. Oh, here they are. Now, one moment, I'll switch here. Not here. I'm switching here. It's my example of AC network. Now you can see how I solve network in reality. What I told in this PDF blah blah blah, how it looks reality. I will need to solve what I need to solve. I will need to solve a linear equation system. So I put a known Zeidel solution function from the first to the 38. It's a Zeidel solution as we saw it. We saw it. This part is known. So this also should come here. You saw it. At the beginning, I put as Zeidel function. I will need to solve a linear equation system. Nothing special. Next. What's this? We saw it somewhere, no? Here it is, my network first incidence matrix. My network topology now as a matrix. Contours as a matrix. EMF vector as a matrix. Current sources. Now what about your omega? Frequency 100. Wait, example. Here I use complex function to create a complex frequency. Complex function weighs two arguments, real part and imaginary. So here is real part 0, imaginary double P multiplied by frequency. As a result, I will get your omega for 100 Hertz. Look how I use it with the resistance vector. Multiplied. Here I have your omega multiplied by 10 millihenries. Here I have capacitance of 31 microfarad. Here I have 20 millihenries, 32 microfarad. As you see, at the moment I have what I did. I have defined this complex frequency dot omega. Everything goes extremely because in CILA I can use mass equation inside array definition. I write it as I should, but we take here on one moment until there are no inductance. Resistance will be resistance. Coil will be capacitor will be 1 against omega. Everything simple. But at the moment you have cowboy branch. Let's say this is and this is K. That AK will be equivalent to KA and equivalent to your omega m. Until you have mutual inductance, your resistance matrix will be pure diagonal. But at the moment you have not own resistance, but common mutual. At this moment, you will have elements outside of the main diagonal. Matrix will be symmetric, but we will see elements outside of the main diagonal. And it may become a problem. It's tiny problem. Very much. Here, look what I'm doing. Diagonal. I knew, but I don't have neutral inductance. If they are present, you need to add these elements after this row. Okay, my work is done. Here, number of nodes, number of branches, it's from Latvian, Mazgurskaits. Number of contours. I need to transpose M and N matrix, nothing complex, just swap rows and columns. To check integrity, again, I can use fact that M multiplied by transposed N should produce a square matrix of zeros. I use it to check, and also I can check consistency between current source vectors. Here, such approach, as I used in DC, is applicable only if there are no mutual inductance. If not, this part should be substituted with what? With Jordan. Procedure we used in transport network. This part is legal only if there are no mutual inductance. If they are present, this part this will not work, and you need to put a complete Jordan procedure here. Okay, let's go forward. I will need to solve a linear equation system. Here I calculate nodal admittance matrix, 3 elements. How I solve a linear equation system? With the same technique. Easy. So I'm getting voltage, I'm getting branch currents with the help of Ohm's law. All these parts we already saw it in DC. It's very easy. The only moment all these elements are complex. For contour currents, same thing. You can see it's very easy. Contour resistance matrix, contour EMF matrix, and call of the Seidel procedure to solve a system of linear equation. Real currents, easy. I can check difference of methods with the max difference. Power balance. Here, be careful. For DC, I can use square of the current multiplied by resistance. For AC, I will get a nonsense. I need to get a power of branch. I need to use current multiplied by conjugation of current and multiplied by branch resistance. Again, non-mutual inductance. Active power. Again, don't forget what I need to get a right sign of imaginary part. I need to apply a conjugation. Current sources. Conjugated current of the current source multiplied by node voltage. That's the way to calculate power correctly. Display here. Very easy. Kirchhoff current at voltage law. And last step, when I solve contour current equation system, I get current. If I need voltage, I can use this, but it is easier to solve a linear equation system. So I will use a Zeidel for the third time, just to get voltages from the current and compare them with voltage obtained by nodal voltage technique. It's just to round check. Can I run it? I'm not sure. I can try. Okay, I got something. What I got? Execution, blah, blah, blah. The square matrix of zeros. It's not square, actually, it's 5 by 6. It's a rectangular matrix of zeros. My topology matrices are good. At last they are coherent. Current sources looks good. Voltages. See what I got? My voltages are represented with a complex numbers. Everything looks simple, but there is one key moment. This simplicity, let's say, bought or achieved with the complex plane, so my voltages have an imaginary part. I will get currents also with imaginary parts. Voltmeter, what will be voltmeter reading? This will be voltmeter reading, the absolute values. This is what will yield ammeter reading, the absolute values. But inside of calculus, I will work with complex. Contour currents, real currents, methods difference. 10 digits after the contour. It's good. Power balance. Dissipated power, 297 watts of heat plus, what's this? Imaginary part. It's amount of energy swapping forward, backward. From all this, if you need to pay for this, here you pay tariff for this. It's what meter accounts. And this part, if you take it from the network, and you, for small customers, free of charge, for large customers, 1/10 of tariff. But if you supply to network, if you get a minus here, for large customers, you will pay fine from 10 to 12 of tariffs. They will be fined because here we have problem of stability. And large customers supplying reactive power to network will get fined. Okay, from all this, EMFs 29.8, 8 watts, 267 from current sources. Total balance, you see, 10 digits on active parts and 11 on imaginary. Good. Kirchhoff law. You can see the Kirchhoff current law matrix is real, but Kirchhoff's voltage law matrix is a complex part. Has a complex part. Anyway, Kirchhoff checks nice. Here are my voltages from contour current technique and voltage difference 9 digits after the contour. Looks what I solved everything. Maybe maybe I will add here and and what I'm doing, what will be readings. Currents. So is it complicated? How do you think? What will you tell? Is it more difficult to solve AC network than a DC?
Yes.
I use the same code. The only point I need, what I need? I'll need a complex mass. With this substitution of real sine voltage, what real sine of current is substituted with some imaginary vector being somewhere and casting a shadow on imaginary time x. How the time goes? Time goes up. In Heaviside's idea, here in this faculty, time goes up and we assume voltage as a projection. Light is here, it's casting shadow on my hand, time goes up. In communication faculty, times goes like this. They assume not sine but cosine. And light is from above. Here, the light coming from above and time goes this way. Here, light comes from the window and time goes up. It's a difference between electrotechnics theory and radio circuits theory. Radio theory written for cosine. Why? Don't ask. Core idea is the same. What I need? Do I need something? Why all this fall into my I'm not sure. In, in general, technique is very easy. But don't forget about conductors. They can make your life much more complex. In reality, I need to substitute this with for real. I should run. Sorry. Yeah, off. I don't know. No. What? What's wrong?
Yes, yes, yes. That is true.
Yeah, what? Here. Mm, mhm. It's okay. this way is more correct. I put a Jordan inversion inside. Worked? Yes, works fine. Works fine. Oops, it was my mistake. Here we are. Here we are. Here we are. We will save it. Кого? А. Кого? Алло. День добрый, да, добрый. Добрый день. Азенес 12, первый корпус. Это где большие белые буквы РТУ и Витек на крыше крутится. Нет проблем, конечно. А точно на меня? Там написано Александр Долгицев? Да, точно, странно. Чего же они на какой-то... Вот дебил. Прости, Господи. Угу, спасибо. Да, хорошо. Where am I? What I'm doing? I knew what you asked me. Oh, come on, machine. No. I'm Alex. No. Please, machine. Let me edit the course, because definitely my students would like to see My students would like to see my multitasking is not so. One moment, where are my here? For example, this one. I'll put it to a learning system. So what should
I need to explain this part.
Yes. What do you have in the branch number 1? Wait.
Branch number 1.
Wait. Where is my nice PDF?
Okay.
Where is the branch number 1? Here is the branch number 1. Yeah.
Yeah.
It contains of 1 resistance and 1 coil.
1 coil, yes.
So its total resistance will be what's number 8? Where are you? Not here, not here, not here. Yeah, here it's 18 ohms.
Yes.
And first coil is 10 millihenries. Yeah.
Okay.
So I'm writing 18 ohms plus J omega multiplied by 10 millihenries.
Okay.
And it will look like, where are you? Not Zadel, not this. Okay, it is. I have defined omega,
Okay. Multiplied, right?
and here
Here, okay.
is the first branch resistance.
Okay.
Easy.
And about the second branch, third branch 16 or 6 equal to 16. Okay, done. Now I
Easy.
understand. Yes.
The key moment, this introduction of complex plane, it's imaginary. It's not existing in our world.
Okay.
But introduction of this allows to simplify all other. Or we should fight with the sine, cosine, or endless. With endless trigonometry.
Okay.
It's a hell.
So, and I have this how I can make the matrix because this is
Take a look.
matrix.
We have A and B and go forward. Take a look here.
Yeah, okay.
First,
I make this for the example.
first and second digit. For example, which one we need? 22? 25, for example.
Yes, I make this. This is right. I make this first value.
No, it's not good because A has not enough elements. Take a look. We have versions of A matrix and B vector.
Yeah.
This is A, this is B. For example, we need variant 25. 2, 5, what yields us?
2, 5.
First digit 2, second 5, it yields us F3. Let's take F
And 3. Okay.
and 3.
And I need to choose fully and F fully or
Fully, because A matrix should be square. How can you solve a linear system with non-square matrix?
okay.
It will not. Result will be a space, not an
I need a
example.
full change.
Yeah.
Choose full matrix.
Yeah, you need.
full.
Do I have an example? Wait 1 second.
Because I'm confusing this item.
Something like this. No, it's not good. Which one was? For example, look here. Here is A matrix.
Okay. And
B vector.
matrix. Yes. Similar, same.
Yeah. And this part,
Fully workouts.
it's a Zayden technique applied.
Okay. Sir, I need to choose A, B, C, D. Which one I need to choose?
What's the number of student ID?
17.
17. So go here. First 1,
and
second is 7. So it will be H2.
We got
This one,
this and this is here.
not going something like.
Here I
And
can
this
do.
one, yeah.
Okay. Thank
It's a very it's a very simple cognitivity test.
Because A11, A12, A1.
It's something like this will work.
Okay. We have already solution, right?
We have somewhere.
You already uploaded?
Yeah, but for example, wait 1 second. Where I use it? I have it somewhere, definitely.
This one, right?
Say the solution for this with method. Yeah, you can
Okay.
use it as a template easily. You just take a shader from.
Same template. Okay. Now I can solve.
You have which one? Here a C network.
Okay.
I have see. Here is the definition of Z. I define till the end of function.
Okay.
Wait there. Here, for example, Z function defined, and where is and here used to solve
Okay.
linear system.
And I need to determine, so go up. So. the matrix section.
Matrix, I have here.
Okay.
Here the how matrix are defined. In implicit form.
Okay. Done.
Easy.
Okay. You already uploaded this example, right?
I'm not sure.
Because I.
Okay, you have a DC network example which uses Zeidel technique. Just cut the Zeidel from it and it will be. It is easy.
But this is a AC or DC network?
It's a system of iteration. Because it's real, it will. Do you see imaginary part?
No.
No. So it is. It can be.
It can be DC.
This.
Yeah. Okay, done.
Imaginary part.
It's AC.
It's an AC network. No imaginary part. DC. What should I? Where should I go? What should I do? Where should I go? What should I do? Rain. Rain stopping in an hour. Can I please go to somewhere where there is no rain and no networks? So, do we have any questions?
No.
We have one. You know what? I need to fill attendance list. Telpos, yeah. I need to fill attendance chart. Come on, machine, wake up. Blah. Tash. Today we have.
Not this.
No, this is not.
Today 10:15. Yes.
Wait, one moment. Not so. I'm on. This it throws me into wrong sim. Yep. No. This one should be correct. This one should be correct. Ta. 1, 2, 3, 4. Impossible. All students present. It's impossible. What? Machine. Why it's warning me on out of all students exam? Strange thing happens. Okay. I think it's.
Now the class is over.
Huh? It's enough for today. Or you want to see more currents, voltages, and all of this. Remember what AC values are vectorial. Or you get a nonsense. British standard. Lag means if you have it's current relative to voltage. Lag means Lagging, lead, informant. So lag is inductive load and lead capacitive. You know, next time I will assemble another circuit. I will simulate all possible power regimes. This possible. This
Sir,
can
you
help.
have all the experiment in MATLAB source file. You have this experiment in MATLAB source file
Good question.
because I need.
Do it yourself. Good question.
If you have, send me.
I'm not sure. Maybe yes, maybe not. Because what's this? No, this is not. Wait a second, I need to take a look. What's this? I'm not sure we need S3.